Welcome to the Crazy Hat Chemist. So another video here on equilibrium. Bam! So equilibrium reactions and shifts. We're going to talk about three different equilibrium reaction shifts, and then we're going to talk about volume pressure relationships in dealing with equilibrium. So here we go. Our first one here is the copper complex ion. So for the reaction, here it is. We got a copper, so CuCl4 minus 2. That's a complex ion of copper and chloride ion, and it's an aqueous, and it's green in color. Therefore, that green color right there. Plus 6 waters, that's liquid, produces a copper complex ion. That's a copper 2 hexahydrate, and that's with water, and that is blue in color. Plus 4 chloride ions. Okay, so the Kc for this is, now that is the K expression is the products over the reactants with the stoichiometric coefficients as exponents. What are not included? Solids and liquids. Do you have a solid in this equilibrium? No. Do you have a liquid in this equilibrium? Yes. That is not included in the K expression. So the K expression is products over reactants with the stoichiometric coefficients as exponents, absent of that water. So here it is right here. Okay, you got that copper complex ion, that's a copper hexahydrate in the numerator, times the chloride ion to the fourth power, right, as an exponent of 4, divided by the copper chloride complex ion, and that's to the first power. Okay, so hopefully that worked out well for you. Okay, which way will the equilibrium shift with the addition of hydrochloric acid? Now, we've passed nomenclature by now, so hopefully you should know what the formula for hydrochloric acid is. The formula for hydrochloric acid is HCl, and it is aqueous. Okay, HCl is one of the 7 strong acids. Okay, and because it's a strong acid, it dissociates 100%. Okay, all right, so this is the hydrochloric acid dissociation. It is a unidirectional arrow, as you can see there. It is not an equilibrium. Okay, hydrochloric acid will produce hydrogen ions and chloride ions. So now the question is, I want you to look at the equilibrium reaction there. The copper complex ion reaction, that's an equilibrium reaction. And then look at the hydrochloric acid reaction. Now, find an ion that is a common ion. That is, it's common between the equilibrium reaction and common with the hydrochloric acid dissociation. What is that ion? That is the chloride ion. So if I add hydrochloric acid, I'm effectively adding hydrogen ions, which don't matter, and chloride ions to the equilibrium reaction, which do matter. So I'm increasing the concentration of the chloride ions. So it's like up, up, and away. So I need to shift away from the chloride ions. Now, because the chloride ions are on the product side, in order to decrease the chloride ion concentration, I need to shift it towards the reactants. So think about it this way. Go back to the reactants where you have the green copper chloride complex and water. Those are the two reactants. Those produce the blue copper complex ion and chloride ion. If I shift the reaction towards the reactants in the opposite direction, then I'm combining the products and making the reactants. So, in order to decrease the chloride ion concentration, because I've added too much, I need to shift it towards the reactants. So it's up, up, and away from it. Okay. Consequently, you should notice that there will be a shift from blue to green, consequently, with this addition of hydrochloric acid. All right, which way will the equilibrium shift with the addition of silver nitrate? So silver nitrate, whether you add a solid silver nitrate or aqueous solution of silver nitrate is a salt, because anything with nitrates are salts and they dissociate 100%. This is the dissociation reaction. So I got silver nitrate, aqueous, in solution because it's in this equilibrium, and it's in solution, this equilibrium is, and I get silver ions and nitrate ions. Now I'm going to ask myself the same question that I did with the hydrochloric acid. Is there a common ion? So is silver a common ion in the equilibrium reaction and the silver nitrate? No. Nitrate ion. Is the nitrate ion a common ion in the equilibrium reaction? No. Okay, now we need to look one more step further before we say that there's nothing, there's no change, there's no shift. Okay, and that is we're going to look at the silver nitrate reaction and figure out, is one of these ions reacting with one of the ions that is in the equilibrium? And that most certainly is a yes. And that is the silver ion. The silver ion reacts with the chloride ion to produce a precipitate. Here's that reaction. So I got a silver ion plus the chloride ion that's part of the equilibrium, and that will produce silver chloride, which is a solid precipitate. So with the addition of silver ion, you're actually decreasing and removing the chloride ion concentration. I'm going to show you that here with an arrow going down. That's a decrease of the chloride ion concentration because you're forming a solid precipitate. That will decrease the chloride ion concentration. That's a downtrodden, if you will. So that's, I need to shift towards it. So that's why I'm going to shift it to the right. And you should see a colorimetric shift from green to blue on this one. Okay, hopefully that worked well for you. I just want to remind you that this whole equilibrium thing is a balancing act. It's a teeter-totter going on here. That lady right there, she is balancing on one leg. And she can move her arm or her leg or even the hair, her long hair that's dangling down, and that could move, and then she would have to adjust and form a new equilibrium. That's what's happening here. As I add and I shift the equilibrium, I'm forming a new equilibrium set of conditions according to Le Chatelier's principle. Okay? All right, let's do the next one. Here's the next one, and this next one is a chromate dichromate reaction. Okay, so here's the reaction of chromate and dichromate. So on the reactant side, I have yellow chromate ion plus hydrogen ions produces dichromate, which is orange, and water. Again, we're going to write the Kc expression. Remember, the K expression is the products over the reactants with the stoichiometric coefficients as exponents. But solids and liquids are not included. I have a liquid here that will not be included. And here is my K expression. It's products, and in this case I only have the orange product of the dichromate in the numerator, divided by the two reactants here with their stoichiometric coefficients of 2. Okay, so that's the K expression here. All right, which way will the equilibrium shift with the addition of hydrochloric acid? Now, we already talked about hydrochloric acid being a strong acid. It dissociates between hydrogen ions and chloride ions. Last time we had a common ion of a chloride ion in the previous equilibrium reaction. For this equilibrium reaction, the common ion is the hydrogen ion. So if I add hydrochloric acid, I'm adding more hydrogen ion, and I need to shift away from it. So up, up, and away. Okay? If I add more hydrogen ion, I need to combine the chromate and the hydrogen to form the dichromate and the water. So it's going to be shifting to the left. Sorry, shifting to the right. And I will see a colorimetric shift from yellow to orange. All right, let's do another. Which way will the equilibrium shift with the addition of sulfuric acid? Sulfuric acid happens to be one of the other 7 strong acids, and it is H2SO4. It decomposes or disassociates 100% in solution, and I got hydrogen ions. Again, hydrogen ions is my common ion. So I'm going to add more hydrogen ions. I'm going to shift to the right. I'm going to see the same colorimetric shift from yellow to orange that I saw with hydrochloric acid. Hopefully that worked well for you too. All right, so let's do some more here. Okay, so which way will the equilibrium shift with the addition of sodium hydroxide? Now, group 1 hydroxides and group 2 hydroxides are strong bases. We're going to be talking about acids and bases in the next unit of chemistry here, but you should know the nomenclature if nothing else. But sodium hydroxide is a strong base. Because it's a strong base, it dissociates 100%, and I get this unidirectional arrow. Notice with the hydrochloric acid, the sulfuric acid, and the sodium hydroxide, all of those are strong acids or strong base, as the case may be. Okay, so with sodium hydroxide, I get sodium ions and hydroxide ions. Do I see a common ion? No. Okay, I do not see a common ion in the equilibrium reaction. However, that hydroxide ion will react with one of the ions in the equilibrium reaction. Which ion will it react with in the equilibrium reaction? It will react with hydrogen ion. So the hydrogen ion in the equilibrium reaction and the hydroxide reaction, and the hydroxide will react and form water. So what will happen to the hydrogen ion? It will decrease. So the hydrogen ion decreased. So now it's downtrodden. So I don't have enough. I need to make more. I'm going to shift it to the left, shift it towards reactants. I will see a colorimetric shift from orange to yellow now. Okay? Hopefully that chromate dichromate example worked well for you. Remember, chromate and dichromate are toxic compounds. You don't want to be playing around with those too much, but they are beautiful colors, even in paint jobs. Okay, the next equilibrium shift reaction is a cobalt chloride reaction shift. So let's do this one. Here's the reaction here. I got cobalt hexahydrate 2+ on the reactant side that's pink, and I got cobalt chloride 2- that's blue on the product side. Okay, I got water on the product side, and I got 4 chloride ions on the reactant side. Okay, this reaction has a delta H value of positive 50 kilojoules per mole. That's an enthalpy change of positive 50 kilojoules per mole. So knowing that this enthalpy change is positive, it lets me know if the reaction is endo or exothermic. Since the value is positive, I know that it is endothermic. Since the value is positive, I know which side of the reaction this heat term belongs on. So if it's endothermic, that's heat absorbing, heat requiring, that will go on the reactant side as a heat term. If that value were negative, it would be exothermic and go on the product side. Okay, so now we're going to work with it being endothermic, of which it is. So the Kc for this, that is the products over the reactants with the stoichiometric coefficients as exponents, absent of liquids and solids, that's liquid water is not included. Don't forget about that 4 stoichiometric coefficient on the chloride. And this is the Kc for this. Remember, these are brackets, not parentheses. That's a 4 on that chloride as an exponent, and the other 2 complex ions have 1s. Okay. Which way will the equilibrium shift with the addition of hydrochloric acid? Hydrochloric acid is this. I see a common ion of a chloride ion. That's going to increase the chloride ion concentration. It will shift it to the right towards products, up, and away. That will cause a colorimetric shift from pink to blue. Okay? That means it will decrease the pink. It will get more blue. All right. Which way will the equilibrium shift with an increase in temperature? So if I heat this reaction up, I'm going to heat this reaction up. I will shift it to the right. I will shift it towards products. It will also cause a colorimetric shift from pink to blue, just like adding the chloride ion would. Okay? Now, which way will the equilibrium shift with a decrease in temperature? Again, my decrease in temperature is right here, and I decrease the temperature. I need to shift towards it. Okay, and that will cause a colorimetric shift from blue to pink. Okay, notice that that endothermic positive enthalpy told me which side of the reaction the heat term belonged. And now I view the heat term just like any other reactant or product. And I can increase it or decrease it, but it matters which side of the reaction it is on. That's the important key point right there. All right, so this next one here dealing with equilibrium reactions and shifts is dealing with a volume and pressure relationship. Okay, when considering volume pressure relationships, one must imagine a closed container. Examples of which would be a can of beans, a plunger on a syringe. There's a plunger with a syringe and a needle. Hopefully you get vaccinated pretty soon. Or a piston for an engine, and here is an engine, a sliced view of an engine with 4 pistons in it. 2 of the outside pistons are in the up position. The 2 middle pistons are in the down position. Okay, so as the piston moves up, like this piston moves up, what occurs to the volume inside the cylinder? Well, the volume decreases as the piston moves up. As the piston moves up, what occurs to the pressure inside the cylinder? Well, as the volume decreases, the pressure increases because you're decreasing the volume. Therefore, the volume and pressure is an inverse relationship. As the volume goes down, the pressure goes up. Conversely, as the pressure goes up, as the volume goes up, the pressure goes down. All right. So the shift in equilibrium will favor a volume change and therefore a mole change. If the volume decreases, then the pressure increases, and the shift in equilibrium is toward the side with the fewer number of moles of gas. Moles of gas, not just moles of anything, moles of gas. Okay, the converse is true as well. And so take a look at this piston and this cylinder. It is going down. Therefore, that is, the volume increases, then the pressure decreases, and the shift in equilibrium is toward the side with the greater number of moles of gas. Awesome. Okay, if an inert gas, for example, xenon, argon, or a gas that does not react with either the reactants or the products is added, this increases the total pressure of the system, and therefore there is no change. I.e., there is no shift if there is no change, either right or left, in the equilibrium position. Okay? The partial pressures of the gases in the equilibrium expression do not change, and Q, which is called the reaction quotient, more on this later in some future ones here, is dependent on the partial pressures, which remains constant, and therefore there is no change. Talk to your chemistry professor about that last statement. That is exactly true. That's what's happening. Okay, so just to recap on this here, the volume decreases, the pressure increases, and you're going to shift to the side with the fewest number of moles of gas. Okay, if the volume increases, the pressure decreases, and you're going to shift to the side with the greater number of moles of gas. Awesome. Okay, I am the Crazy Hat Chemist, and of course I am a chemist, and I got this hat from a number of my favorite students years ago. Way long time ago, they went to Disneyland and they got this, and they said, Mr. Montbriand, he's a chemist, of course. Give me a thumbs up if you like that video. Subscribe to my YouTube channel. Look at my website. Get a t-shirt. See you next time. Have a great day. Bye for now.